So today we'll talk about hypothesis testing. There will be a little bit of math in it, but we'll try to keep it very simple. So before we go there, let's talk about evolution of statistical thoughts. The statistics as a field of science is pretty recent, as opposed to biology or chemistry or physics. The Carl Pearson, who is the great grandfather of statistics, died in 1936. So up to the later part of 19th century, the statistics was very minimal, and we basically would do a lot of measurements, but we would only take the measurements that we liked, and we didn't use the concept of distribution. So you take a lot of measurements of, say, temperature, and then we'll take the one that we like and discards the one that we don't like and think of them as a measurement error. Carl Pearson said that yes, measurement errors can happen, but a lot of measurement is a part of the phenomenon itself. So all the temperature readings, you take them, and then they will follow a distribution, and then the population can be described in terms of the parameters. He described 4 of the parameters. That would be your mean, standard deviation, skewness, and kurtosis. So that's the concept of parameters. But Carl Pearson was still doing all, when you are describing a population, you're measuring everybody in the population. Then Ronald Fisher took it a step further. He said that we never see the full population distribution directly, but we observed samples. So population parameters is unknown but fixed, and we estimate it from the samples. And these estimates are random variables, and they on themselves have a frequency distribution. So you have a population parameter which we want to, it is fixed, but it's unknown. We take a bunch of samples and we estimate the population parameters from the samples, and these estimates from the samples, they themselves have a frequency distributions, and that's why this field of statistics is called as a frequentist statistics, because it relies on the frequency distribution of the samples. And these are just mathematical representation. Mu and sigma are for population, while x bar and small s are considered when we're talking about samples. Then we will not talk about Bayesian statistics today, but the main idea is that with frequentist statistics, as we said, the population parameter is unknown, but it's fixed. While Bayesian, and you are estimating the samples. While in Bayesian, the population parameter that itself is a random variable. So you can estimate the probability of the population parameter. So you can say the probability of my result being true is this, which we cannot say with the Bayesian statistics, and we'll talk about that in a little bit. Okay, just going over this definition one more time. Variables are the quantities from the individuals, so like blood pressure, heart rate, cholesterol, etc. Parameters are the properties of a collection of individuals, so mean blood pressure or heart rate, and for a sample, these properties are called estimates of the population parameters. Okay, we talk about distribution a little bit. Distribution, we'll have deviations in whatever we are measuring. When you run an experiment a number of times, you get a scatter of numbers, and these are called the distribution. To define the distribution, you use the parameters, and they have 4 parameters. That's the mean, standard deviation, symmetry, and kurtosis. Mean and standard deviation are pretty easy to understand. But this is skewness, so this is a positively skewed data, and this is a 0 skewness, and this is a negatively skewed data, and all the values are on the right side. And this is kurtosis. Kurtosis, they're all normally distributed, but this is based on how big the height is. So the mesokurtic, leptokurtic is tall, while platykurtic is flat, it's more spread out. So these are skewness and kurtosis. They can all be mathematically represented also. Okay, so next is normal distribution. We all know about normal distribution. Normal distribution is a distribution where mean, median, and mode are the same. Skewness and kurtosis are 0. Normal distribution is very common, but not so much in medical research. However, we use it a lot because it has very nice mathematical properties. If you start doing mathematical tests, normal distribution, if two random variables have normal distribution, then their sum also has normal distribution, and all kind of sums and differences of normal distribution have normal distribution. So you can do all sorts of calculations. Multiplication, they're not multiplication is not normally distributed, so that's where some of the errors happen, but we don't need to go into all that today. Okay, so this is a concept that you probably know from junior high school statistics or high school statistics, and that is about how we calculate the probability from a distribution. So let's think of a point. Start with a point on the x-axis and figure out the corresponding area or probability under the curve. So to do that, first thing you have to convert is to change the point on an x-axis to a standard normal value. And how do we do that? That's the z observed, that is xi minus mu, that is mean divided by sigma. Say x is the body mass index and xi is the individual person's value for the body mass index. And we want to convert this value to a standard normal value. So that is how you will convert the value to a standard normal value, because the xi, that person's body mass index, minus the mu divided by sigma will give you the standard normal value, and that you can then do the distribution by using the applet. So example, if the mean BMI is 24, standard deviation is 3, BMI more than 29.9 is obese. And we want to find the proportion of people in this population who are obese. So we want to know what is the probability of x is 29.9. So first we have to convert the 29.9 into a standard normal variable, which is 29.9 minus 24 divided by 3, or 1.97. Now all we have to do is probability of x more than 29.9 is same as probability of z. Now we can't do anything about 29.9, but we know what z of more than 1.97 means. And how do we find that out? For that we need to do a applet or z tables. You can do it with the z tables also. So we go into, let's see if my thing will work. It will not want to work on this, but basically you go into one of these applets and it will give you a z of 1.97. It will give you a probability, so you can calculate that about 2.4% of the population is obese. What happens if you do not know the full population? And that is what typically happens, because previously we had used the population mean, but most of the time we don't have population mean, so we have to use what is called as the tree distribution. Tree distribution is very similar to the z distribution or the normal distribution, except that its kurtosis depends on the sample size. So if you are large sample size, it becomes more normally distributed, and then as it becomes smaller, it becomes flatter. So z observed is xi minus mu upon sigma, while t observed is xi minus x bar upon s. And t distribution changes with the sample size. When you use a t applet, it also asks for a degree of freedom. So the probability of your value will change based on what the degree of freedom is. And so example, some 35 patients, the average rate is 145 pounds and standard deviation is 30. One of the patients, Zeke, weighs 175 pounds. What proportion of patients weigh more than Zeke? Right? So 35 patients, average weight is 145 and standard deviation is 30. One patient has 175 pounds. Now we want to know what proportion of patients weigh more than that patient. So x bar here is 145, which is the sample mean, and the s, small s, is 30. T observed, it will be 175, that is xi minus x bar, which is 175 minus 145 divided by 30, which in this case is just 1. And now we also need a value called degree of freedom, which is 35 minus 1, which is n minus 1. It is another science in itself, while degree of freedom is not n, but n minus 1. But for now, we'll just say that degree of freedom is n minus 1, and then you go to the same statistical table or surfstat, and then you find the probability. In this case, the probability is 16.2, but you can play around with it. If the degree of freedom is 4, then the probability would be different, while the degree of freedom is 10,000, then the probability would be different. So the point is that the probability of you finding that result depends on the sample size. Okay, so that's enough of that. Then we'll talk a little bit about central limit theorem. Central limit theorem is very important for whatever we do, and this is the reason why most of the tests actually work. The theorem itself is that if you take a lot of samples from the population and calculate their means and plot them off a graph, their distribution will be normal. Even if the distribution in the population itself is not normal. It's typo here. Even if the distribution in the population is not normal, the sample means would still be normally distributed, provided the sample size is large enough, which is there's a lot of math behind this, that's why 25 gives you that number, but most of the time the rule of thumb is more than 25. So average of a large collection of numbers have a normal distribution regardless of the normal original distribution. Variance of the sample is sigma square. Variance of the sample mean is sigma square divided by n. Standard deviation of the sample mean would be sigma square divided by under root n. So the bigger the n, the less of the variance, and the sample mean would approximate the population mean. This is a example of how we do it. So I will stop talking because I've recorded this previously.
So this is a small illustration of how the central limit theorem works. So for example, we have this population, and population we are taking the weight. Say this is weight in pounds of the population, so it says skewed right. A lot of them have the weight around 80, but some of them have weights all the way up to 160. So this is by no means a normal distribution. The mean of population is 100 and standard deviation is 15. Now we want to take samples out of it. So we are taking samples of 25 random people, and we take one sample, and then once we see what happens when we take one sample, this is the sample and this is just the distribution. So some patients or some people, this many, 5 of them are between this weight range, and so this is the histogram of the weight distribution for that sample, and this is the sample mean. So mean is 104 from this sample, and standard deviation is 18, and there is one sample. Right now the means of sample means is also 104 because we have just one sample. Now let's draw multiple samples. So we keep drawing samples, and this is the distribution of the sample means. And so you can see that as we draw more and more samples, we have now 8 samples, and as we keep drawing samples, we will the mean of the sample mean is approximating the population mean, and the distribution, which was nowhere near normal distribution, the means of sample means is still normal. So we have, the more samples we draw, the more normally distributed this will start looking. So we have now 100. See, we got 200. It's like exactly normal distribution of a. Now anybody can say that this is a normally distributed data. So this is
okay. So
so this is a small illustration of how
Okay, so we talked about normal distribution and the central limit theorem. Now let's move on to the confidence interval. Confidence interval is a term that we use very often. Confidence interval introduced by Jerzy Neyman. This is another one of the very founders of modern statistics, and he introduced this in 1934 as an interval estimate of the statistic, and call it a confidence interval. 95% confidence interval we use very often. This is another concept that I want to be clarify here, that it does not indicate that the parameter of interest has a 95% probability of being within the interval, which is, we often think of it that way, but it's not true. Rather, it means merely that infinite number of samples were taken and confidence interval computed. 95% of the confidence intervals would capture the population parameter, and confidence interval do not provide a strong case of concluding that the population parameter of interest is within. So we say that, oh, the mean of our sample is this with a confidence interval of this and this. What we think it means is that the actual population parameter lies between this and this, but that's not true. What it means is if we take infinite samples, 95% of them may contain the population mean, and we will describe that with another little illustration next. So this is another video that I will run.
So this will be an illustration of confidence intervals and what do they mean. So we have a population mean of 100. Say we are measuring a characteristic of the population, which is continuous variable. In this case, it's IQ. Population standard deviation is 15. And we are taking a sample of 25 from this population. And right now we have one sample and we are calculating the confidence interval, 95% confidence interval. So as we said, 95% confidence interval means that if we take infinite number of samples, 95% of them will contain the population mean. So let's see, we take one sample and this is a sample which is mean is 97, standard deviation is 15. We just took one sample, so this sample turns out that their confidence interval contains the population mean, which we know in this case it's supposed to be 100. Most of the time we don't know this, or almost never we know this, but in this case suppose we know that the population mean is 100, so this confidence interval this population mean is within this confidence interval. But let's draw additional samples. So we draw another sample. This one also does have a population mean. So right now we just have two, so we can't really make any assessment out of it. Both of them contain the population mean. But as we draw additional samples just out of statistical reasons, so this turns out this confidence interval does not include the population mean. So there's nothing wrong with that sample. This is just how statistics works. This one does not have the population mean. So that means it's one of the reasons why you cannot say that the 95% chance that the population mean is included. It just means that 95% of the samples will include the population mean. So let's just keep drawing samples and see what happens. So as we keep drawing samples, this is like only 91, but we have only 12 samples. As we keep drawing, and it's based on infinite number of samples. So as we are drawing right now, it's 92, and it keeps changing because there are some samples which do not contain the population mean, but majority of them contain the population means. And as we can go up to 100, it's not infinite, but as we go to 100, you can see that 95% of the confidence interval that contain the population mean. Okay, so this will be an illustration of
So after this, we'll talk a little bit about the actual hypothesis testing and the p-values. So one of the very often reported um, history behind how Fisher came up with this idea of hypothesis testing or p-values is this story that you was with a group of people and there was some lady who mentioned that she can, when was drinking tea, she can differentiate whether the milk was added first versus the milk was added later on into the tea. So they designed an experiment, and the null hypothesis is that the lady cannot identify correctly and she's only guessing, while the alternative hypothesis is that she can identify correctly. If n is 1, if you did it just once, there is 50% chance of her ability to identify versus guess. But if you do it 20 times and she's correct only one time, then she was right 19% of the times. So the probability of observing this result, that her being right 95% of the time is this result, if she was only guessing, is only 5%. So the null hypothesis being correct is only 5%. So the probability of getting this data, the null hypothesis was correct, is 5%. So that's sort of the theory behind all of these experiments and the p-values. So that's p-value. P is the probability, but the probability here is probability of finding a difference of this size or more by chance. That's what the probability p-value means. We have decided that 5% is okay, statistically significant in all circumstances, but there's no like science behind it. Earlier reports on p-values were by Fisher. However, he did not establish the 5% rule. We credit this to Jerzy Neyman, who did this frequentist distribution of probability in hypothesis testing, and he discussed the 5% probability. Unfortunately, it has become coded, and then when we say statistically significant, we say, oh, the p-value is less than 5. That's why it's statistically significant, but that's just convention rather than science. So why 0.05? It's a number, an arbitrary number. So you have to go back to the theory in like 1940s, and even when I was doing medical education in 1990s, you would do this test, and then you would have in the back of the book they would have the tables, and the tables would have a p-value for 0.05, 0.02, 0.01. So you can't calculate the p-values like now with an infinite resolution. So statistic critical value were given for specific levels only, so that tends to become, we have to apply some number, so 0.25 or 0.01. So this started as a convenience, but then it became a red line that it has to be 0.05. So there's another important concept of p-values and sample size, and this is important to understand, because any difference, if it is large enough, will come up as statistically significant, and a very large difference, if the sample size is small, will not come up as statistically significant. So this is a description from Andy Field's book. We're measuring self-esteem in two groups, and intervention is hugging a teddy bear box versus a teddy bear itself, and we did a sample size of 10. This is hugging a box, and the self-esteem is 11, and the teddy bear, as we have seen before, the confidence interval becomes wide when your sample size is low. So the mean is 15 when you hug a teddy bear, while the mean is 11 when you hug the box. And you can say that there is no difference because the confidence intervals of the two populations overlap each other. But when you do the 100, the mean is exactly the same in both of them. However, this will come up as statistically significant. So exactly similar result will test statistically significant if the sample size is large enough, and even minor irrelevant differences will return significant with a very large sample size. And then there are certain pitfalls that you have to avoid while doing this null hypothesis significance testing. One of that is multiple testing. The more significant test you do, the more likely that you will come up with a significant test by chance. The number of tests is 1, that at least one will be statistically significant is 5%, is 2 is 9.83, is 14.3. So it goes up very, very quickly. So that is called the multiple testing. And there is a math behind it. If you do one test, the chance of one test having a p-value of more than 0.05 by chance will be 0.95. And then you do two tests, the probability of both the tests having a p-value of more than 0.05 by chance will be 0.95, 0.195. The chance that at least one test has a p-value of less than 0.05 will be 1 minus this probability, so that is 1 minus 0.05 square, and that is called the family-wise error rate. So this is how you come up with that number of 9.8%. It's not just one is 0.5%, the other is not 10%, and then it keeps changing. So that's your math behind multiple testing. Then how do we fix that? We fix that by doing what we call as Bonferroni adjustment. So overall type 1 error rate across all comparisons remain at 0.25. And the easiest way is to divide the alpha by the number of comparisons. So if you're conducting 10 tests, then we use 0.005 as our criteria. So the cumulative type 1 error rate remains below 0.25, but there's a lot of arguments against it, and because there is a lot of statistical power in detecting this. So obviously, you make it less likely to get type 1 error, but you're more likely to get type 2 errors. Right, then there is a concept of p-hacking. This is looking for statistical significant relationship in the data. Then you have a lot of analysis, and then just look for whatever is significant, and then just mention that out of thousands of tests you do. So that's p-value that is looking for anything interesting in your data after you look at the data. And then p-harking is hypothesizing after the results are known. So remember, when we did the lady testing T experiment, we hypothesized before and then we run the experiment. We don't run the experiment and then go back and do the hypothesis. So if you already know the results, then you don't go back and hypothesize. But it is unfortunately very easy to do that. You see the results and say, oh, this result is looks interesting, and then you make an hypothesis in retrospect, and then you write the whole paper based on that was your original hypothesis. So that's called p-harking. So example, we are measuring happiness by sex, gender, age, political affiliation, and other 20 variables. So this is male and female and their p-value, and then young and old and their p-value. The only final difference in the p-value for age. Record only this p-value and do not mention that another 19 analysis you have done in the manuscript. This is called p-hacking. And when you find a significant impact of age on the happiness, then you go back and make an hypothesis and then write a paper as if that was your original hypothesis. That's called p-hacking. So both p-hacking and p-harking are not good science. It's very easy to do these things these days because it is so easy to do multiple testing now with computers. But always be mindful that that you're not doing p-hacking or p-harking when you are completing your analysis. And there's another thing that p-value is not comparable across studies, which is also, this study had a p-value, this drug has a p-value of 0.04, while the other one has a p-value of 0.001. So the difference of 0.001 is more than 0.04, or it's more significant. So there is nothing like more significant in terms of the exact null hypothesis significance testing. So example, we are testing two drugs. This is the standard number of patients 10, mean decrease in blood pressure is 5, standard deviation is 1.5. Drug A, you use 10 or just control, mean decrease is 6.5 and standard deviation is 0.5. Drug B, also 10, mean decrease is 15, standard deviation is 12. So mean decrease by 12 by drug B is much higher than drug A. And then when you do direct comparison with drug A, it is also superior in decreasing the blood pressure. But if you compare with the standard p-value of the drug A, will come out to be 0.008, while the drug is only 0.022. So you can say that the drug A is better because the p-value of drug A is lower, but when you do compare the drug A with drug B, you will find that the drug B is superior. So p-value is about inference, it's not about estimation. It does not tell you anything about the strength of the evidence or the size of the effect for that matter. Then there are some ASA statements on the p-values. P-value indicate how incompatible the data are with a specified statistical model. The smaller the p-value, the greater the statistical incompatibility of the data with the null hypothesis if the underlying assumptions used to calculate the p-values hold. P-values do not measure the probability that the studied hypothesis is true or the probability that it is produced by random chance alone. So this is very important. P-values just tell you how incompatible your data is with your null hypothesis. That's it. It does not tell you whether or not that particular study or value is incompatible with the population metric. Scientific conclusions or policy decisions should not be based whether a p-value passes a specific threshold. This is opposite of what we do currently, and proper inference requires full reporting and transparency and does not measure the size of an effect or the importance of the result. So that's all the, I mean, we will still use the p-values. I still use the p-values, and it's okay to use p-values as long as you know the potential problems with it. And there are solutions for it, and I've done a ground round on it called on Bayesian statistics. We're not going to go in that today, but most of you will complete your proposals and present it, and you will be doing this kind of frequent test analysis. Either you will be doing it, or statisticians doing it, or I'm doing it, which is okay to use as p-values. And it's okay to even read the p-values which is reported in the literature, but be mindful of what actual p-values mean. Thank you.